All right, so welcome back to part two of investigating how voltage and current work in series. Now, last time we looked at three identical bulbs and how they reacted when we wired them in series. And what we saw was that the amount of current flowing through them was the same. If you remember the definition of being in series, it just means in the same path of current. So that principle there is kind of in the name, right? Series, same path of current. Series, same current. But what we did see is that they will divide up the amount of voltage that's being applied to that branch. Right? So we would say that those three bulbs would have been in series, so meaning they're all in the same branch. So a branch is a path of current. And in this case, we were applying 6 volts to that branch, and they shared it. So in fact, they didn't just share it, they shared it equally. Each one of these got about 2 of the 6 volts being applied. So it's kind of like going off that idea of conservation of energy. This is the amount of energy being supplied, and these use that energy. And we remember that energy can't be created or destroyed, it can only change forms. So we were converting that 6 volts into light and heat in the light bulbs, and if we applied 6 volts, we could only use 6 volts. And we saw that those happened equally, but that's not always the case. And what I've got here are 3 little resistors. And each of them are rated for 5 watts. I'm going to try to show you that real close here. So this one is a 10 ohm resistor, and it's rated at 5 watts. So what that means is up until 5 watts of power being consumed, this will remain ohmic, and it will actually remain safe to use. After that, it will start to heat up so much to the point where its resistance will not be that same 10 ohms anymore, and it could cause some very bad things to happen if you're not careful. These ones are also rated for 5 watts. I've blurred out their amounts of resistance, so we're going to use our multimeter to check that. So if we go over here to our multimeter, you can kind of see that there's a lot of different things on the dial that we can set it to. Actually, I'll just hold it up here. So there's a range of voltages we can set it to. So this is DC voltage that we can measure. We can actually measure AC voltage as well. But this whole range here allows us to just measure the resistance of resistors that we don't know if we have some unmarked ones. So what we'll do is we will set that to, we'll set that to 2,000 because I know nothing here is over 2,000. Actually, we'll set it to 200 because I'm pretty sure nothing here is over 200 ohms. It's kind of like your limiting factor there. We'll put this back over here. We'll set that back up so we can see those. And just to test it out, we will test the resistance across the 10 ohm resistor just to make sure it's working properly. So we go this, and yep, so we see about 10.2 ohms, but 0.1 ohms isn't going to make a real big difference. So in fact, it's settled all the way down to exactly 10 ohms. So we got a 10 ohm resistor here, and then our single one here that's colored red, this one is this one's about, 96. So we're going to round that up to 100. We're going to call that a 100 ohm resistor. So we got a 10 ohm resistor, a 100 ohm resistor, and here we're going to measure this here at, so it's about 48.5. We'll round that up to 50. Right, so if we go right to the ends of the, because if we include that, we're going to get, like right about there, just about 50 ohms. We could do the same thing with this one if we test right at the ends. Let's see here. Yeah, that should get us closer to 100. So just about 100. So we'll round up. And what we will do first is we will hook this up. So we got 6 volts going to 10 amps. 6 volts going to 10 ohms. How much current is that going to be? Let's see, 6 volts going to 10 ohms. Ohm's law, V equals I times R. Voltage equals current times resistance. So voltage will divided by resistance, 6 divided by 10 should give us about 0.6 amps running through this right now. And what we're going to do now is we're going to wire it in series with this next one. So actually we're going to go with this one, the 50 ohm resistor. So now we've got 10 ohm resistor and a 50 ohm resistor. So that's a total of 60 ohms of resistance here. So let's see. So now we've got 60 ohms of resistance with 6 volts. The amount of current should be, let's see, 6 volts divided by 60 ohms of resistance should be about 0.1. Hey, 0.1. Awesome. That works. But let's take a look at how the voltage is being distributed. Right? So now we've got 6 volts that we're applying. And if we use our trick that we learned in the last video, if we measure across both the resistors, we can see how much total voltage is being used. So if we go to this probe here and this probe here, we can see that we didn't measure forgot to switch this over to voltage again. There we go. Cool. So if we measure the voltage across these, we are seeing that we are getting the 6 volts that we're supplying there. But now let's see how much each one gets. So let's see. So this one is getting 1 volt. So the 10 ohm resistor is getting 1 of the 6 volts. Where here, the 5 ohm resistor, sorry, the 50 ohm resistor is getting about 5 of the volts. Well, the rule we came up with last time still seems to apply, right? 1 volt here, 5 volts here. We're using a total of 6 volts. We've got 6 volts there. But they're not dividing up equally. Well, let's also remember, right? So this is a 10 ohm resistor. This is a 50 ohm resistor. And we got to remember what a ohm is, right? It's a volt per amp. So it means that this would need 10 volts to get 1 amp of current flowing through it. This would need 50 volts to get 1 amp of current flowing through it. 50 volts for the same amp, 10 volts for the same amp. This needs to use 5 times as much voltage as this to get the same current flowing through it. Well, they're wired in series, so that means the same current is flowing through it. All right, well, if this one has 5 times the amount of resistance, what that means is it needs 5 times the amount of voltage as this one to have the same current flowing through it. In series, same current, so this is going to get 5 times as much voltage as this one. So this one had 5 volts, this one got 1 volt. If this one got 1 volt, 1 times 5 is 5 over here. So it's still kind of obeying Ohm's law and going off of like what resistance means. It means how many volts do you need to get the same amount of current flowing through it. So let's try and swap it out for the 100 ohm one. Let's see if that still holds true. All right, so now we've got 110 ohms. All right, so 6 divided by 110 will give us, I'm not going to do that math in my head. Hopefully you did. About 0.05 amps. And let's see if that holds true, right? So now we don't have 5 times as much resistance, we have 10 times as much. So whatever this is, this voltage should be that times 10. Let's check to see if we're still getting our full voltage. Yep, we're still supplying 6 volts. We're still using 6 volts. So now, if this one is getting half a volt, this one's got to be getting 5.5 volts, so 10 times as much. Well, wait, is that 10 times as much? 0.5 times 10 should just be 5 volts. Let's turn the sensitivity down on this. See, when we do this, what I did is I switched my maximum amount of voltage from 200 volts down to 2 volts. And what that does is it gives me more decimal places so I can get a more precise answer of how many volts this thing's actually using. So what I can do is I can test that now. So I can test across this one here, and we can see that, oh, check that out. It is closer to 0.5 volts, right? Right across here, we're getting about 0.55 volts, right? 0.55. So now if we check across this one, 0.55 times 10 is, hey, look at that, about 0.55, 5.5. So again, the numbers aren't completely perfect because we're dealing with such different amounts of resistance here and the wire resistivity, but the idea still holds true, right? So this one has 10 times as much resistance as this one, So this one gets 10 times as much voltage as this one in here. They're still sharing it. The total still added up. Is this one hot yet? No. Okay, good. The total still added up to 6 volts, but they'll share it based on their resistance, right? The things with more resistance get a bigger piece of the pie. And the last thing we'll do is we'll put all 3 of them in series, and we'll see what that does. So now we've got 160 ohms of resistance total. And what you can do is you can see how much total current there is for that. Right? So if we've got 6 volts and 160 ohms of resistance, that should give us a total current of about 0.03 amps. And that might be just a rounded off number because now we're dealing with such small amounts of current that that'll go there. But what we can do is we can measure this again. In fact, you know what? Let's do it this way. Let's turn this off. Let's crank this up to something a little bit more that we can handle. So it's double. In fact, let's see how much we can go. I think we can go all the way up to 18 volts. So let's do that. So we got a full 18 volts here. So 18 volts divided by 160 ohms gives us about 0.11 amps. So that's probably rounded off. But what we can do is we can take a look at this again, right? So this one here is getting 1.1 volts. This one here is getting, so now we're up to 6.6 volts. And now here we're up to just about the full 18 volts across these three. So it's rounded off a little bit. In fact, you know what? Let's try to see if we can, let's put this here. Let's rest this one here. So we're getting 17.8 volts. So I'm going to crank this up so we can get a full 18 right across. Yeah. So this says 18.1, but what we're doing is we're just accounting for the wires here. So now we've got a full 18. And what we should be able to do is use our same rule that we were using before, right? So this one here is getting 1.1 volts. So let's see. This one has 5 times the amount of current, 5 times the amount of resistance. So it should be getting 5 times the amount of voltage. So 1.1 times 5 gives us 5.5. And then let's see, if this is giving us 6.6, or rather 6.7, we should be able to just use Ohm's law to figure it out, right? Or rather how voltage works in series to figure it out. If we've got 18 volts that we're supplying, and we're using 6.7 here, 18 minus 6.7 should be 11.2, or but it probably should have been 11.3. But again, we're just kind of rounding here because when we go across, we've still got the full 18. But check this out, right? So this is 11.2. This down here is 1.1. 1.1 times 10, right? Because this is a 100 ohm resistor. So this has 10 times the resistance of this. So if this is 1.1, then this should be 11.1. Or in this case, 11.2, because we're rounding off. Right? We could go back down, increase our sensitivity here, and we could see, yep, so like 1.149-ish. Yeah, sliding these across. But again, taking wire resistivity and everything into account, it still holds true. Everything that we just learned holds up. So the two main rules we're looking at is how voltage and current act in series. And so we can see that current in series is just going to be the same throughout, kind of just by going by the definition. And hopefully you saw that by hooking up the ammeters in place, where no matter where we put the ammeter along this path, we got the same amount of current. And voltage, the way it works is that it's shared, right? They're going to share whatever voltage is supplied to that branch. If they are identical resistances, like the light bulbs were, well, then they'll share it equally. But if they're not, they're going to share it proportionally. Things with more resistance are going to get more of the voltage. Right? We put these here. This had 10 times the amount of resistance as this one, so it got 10 times as much voltage. This had half the resistance of this one, and it got about half the voltage. This had 5 times the amount of resistance as this one, and it got 5 times the voltage. And that is how voltage and current work in series. And by work, we mean behave. That's how we observe them to behave, and we can kind of come up with our rules and laws based on them.